Hello students. So we are going to now start the lecture number 10 of this course on nanostructure materials, characterization and properties. Well, I have started discussing about thermodynamics aspects of nanomaterials in the last lecture. And prior to that, I discussed about surface energies and related aspects. We are going to come back to surface energies after we discuss about thermodynamics, because some part of the surface energy will be related to the derivations and the equations which I am going to do in the next couple of lectures and including today's one. So what the last lecture, what we do, we learned something about thermodynamics of nanomaterials, okay, and we shall learn more because nanoscience has basically changed the way we look at thermodynamics. So what we did actually in the last lecture, let us kind of recap first. I did two important thermodynamic derivations. First one was what? First one was about the effect of size and curvature on the temperature, basically melting temperature. Okay, effect of size and curvature, and they are related, as you know. Curvature is 1 by r, where r is the radius of the particles, right? So what I derived? Effect of curvature and size on temperature, basically melting point. I derived the relationships where T of the melting temperature of the particle with radius r is equal to T equilibrium temperature of the particle which is a large size. That's what I write superscript infinite, okay? And this is multiplied by 1 minus a factor gamma BB kappa. This is gamma, this is V. Gamma is surface energy, V is the molar volume of beta phase V. Actually, it can be any phase, by the way. Kappa is the curvature, and delta H is heat of fusion. So you can see that this gamma B beta, basically kappa by delta H, is a fraction, okay, and this obviously will be a factor R, right, which I didn't put intentionally, so you can write down. So as the R decreases, this factor actually increases. So as the factor increases, 1 minus of this factor decreases, and therefore the melting temperature of a particle of radius r decreases. That's something which you have derived using very simple concepts, which will again do that. That's the first thing I did. What is the second thing I did? Second thing I did is this effect of what? Curvature on vapor pressure, right? Every element at atmospheric pressure is equilibrium with its vapor pressure. That's a liquid solid, right? It doesn't matter what the temperature, but there is equilibrium between these two. That's why they're stable. Well, now this vapor pressure is also a function of size, right? So we derived a relationship P R. Again, I am putting R in everywhere, which is not there in the previous description, to differentiate that this is the vapor pressure of a solid with a radius R is equal to P 0. That's the vapor pressure of a material with the bulk size exponential gamma P beta kappa. Okay, yeah. Now I can see right. So, the first equation, this r will not be there because kappa is equal to r, 1 by r, right. The kappa is equal to 1 by r, that is the radius of curvature. Okay. So, let us write 1 by r the way I have written, so that, right. So, that is how actual. So, vapor pressure increases very rapidly, this is an exponential function. So, this is exactly what I discussed. Now, I want you guys to derive these equations from the basic fundamental thermodynamics. Okay. And basic fundamental thermodynamics is what? This is the fundamental equation, okay, which you should know. The total differential of Gibbs free energy is equal to B dP minus S dt, where P and P is the pressure, T is the temperature, these are all set variables, volume is V and entropy is S, right. This is the fundamental equation I used in all derivations of this, nothing else, and I derived this equation at the beginning itself of the last lecture. So, please try your hand on this equation to derive it, because this is very important for you to know and you should not forget it. Obviously, please do collect your questions, and whenever we will come back, I will like to answer the questions if you have any. Okay. So, now we are going to switch over and start discussing about something about new things, right. That is what I wrote. We will be talking about another glorious day. You can clearly see the two sea lions are moving in an Arctic ice water mixture, where these are the pieces of ice and this is the water. And they are wondering how come ice is floating in the water, what is the stability of these two, okay? What dictates the stability? And that is something we should be knowing very well, because thermodynamics is something which reserves its opinion about impossibilities, right. So, here pieces of ice are in equilibrium with the water, seawater. Seawater has a lot of salts, right. And what dictates that equilibrium at the interface between this ice and the water? Have you ever asked this question to yourself? I think we should discuss. In a hot summer day, you may be thirsty, you are at home, you open your deep freeze and pour little bit of ice from your ice tray into the water, and slowly you will see the ice is getting melted down because of the temperature in the summer day, right. But for few moments the ice pieces will remain in equilibrium with water, although slowly the equilibrium will be getting disturbed and the ice will melt to water, but still few moments you will see that. In the Arctic, temperature is sufficiently low enough to have this equilibrium staying long, at least before the dawn of the summer in Arctic, right, or in Antarctic, right. So, what does actually dictate this kind of equilibrium and how this can be interpreted? Okay, that is what this guy at the big back is saying, speed up in the front or we will miss the lecture of Professor Biswas, right. Okay, they may be stupid enough to ask these questions. Who wants to listen to lectures of the professor, right? Okay, but they are interested. Some guys are there in the class will be interested always. Well, the front guy is saying, I know, but I am trying to figure out how we can describe this two-phase one component system in terms of measurable parameters. And what are measurable parameters? Temperature and pressure. You can't measure other things in terms of that, temperature, pressure and volume, right, but they are related, but two independent variable, temperature or pressure, or temperature or volume, or pressure or volume, right. So, he is saying, I am trying to understand it, although we are going to attend the lecture, let us go back and ask this question to professor, right, what you can give. The guy at the back is said, what a Greek you are, you must rapidly move, okay, these are none about business, okay, why you are interested. This is something which always happens, when you are students also, we used to do that things. Before going to the class, we used to think, what the professor is going to teach. It may not be understandable to us. That's what it is. So that's what I say. Welcome to another glorious day of nanomaterials. Okay, you know Gibbs free energy calculations, right? What is Gibbs free energy? This energy freely available to you to do the work. If you are a system, that is what it is. For any system, it is energy freely available to do the work. And we know that Gibbs gives this fundamental equation, G is given is equal to H minus Ts. Right? This is a fundamental equation. Please do not forget it, even at the end of the semester also. Okay. G is the Gibbs free energy equal to H, the enthalpy, minus T, temperature, multiplied by S, entropy. Right? It is very easy to do that. Okay. Many people define in many ways, but I am not going to those things. There are many ways you can remember it. Okay. But best to remember is H minus Ts. H is the total enthalpy, total energy of the system. Enthalpy is the Born energy of the system minus the thing which is not recoverable, that is the entropic part. Because entropy is 1 by temperature, that is why to make the units okay in the both sides, you have to multiply by temperature. Right? That is what it is. So this part, he knew long back that this part is not usable. This part is gone in the system. You cannot retrieve it. So that is why you have to subtract it. Well, that is a very fundamental law, fundamental equation actually, which is dictated, which will dictate almost everything in the world. Okay, this aspect of this can be used even the stars, to oceans, to rain cycle, to carbon dioxide cycle, everything you can discuss with us. This is a very fundamental equation. So we know that G is a function of temperature and pressure both. If you consider pressure to be 1 atmospheric pressure, that is what done in metallurgy. Okay, sorry about others. So then it's function of temperature is equal to HT. This is also function of temperature minus TST. So this looks like a equation related to temperatures, right? Now H is related to Cp actually. Cp is heat capacity. You already studied in the second year of bachelor's, or maybe if you have not, please go to any books of thermodynamics like Gaskell, G. Gaskell, or maybe another thermodynamics, lipids. Okay, correct. That's equal to minus dH by dt. So that's if you know Cp, you can calculate the change of enthalpy, that is dH, and then if you integrate that, you get the enthalpy of the system. So what do you need? You need basically that's give change of enthalpy. So you need a standard state to get the actual value of enthalpy, but you are not interested. We are interested in change, right? You have seen that most of the equation, what you are interested is this, del G. Del G is equal to del H minus T del S. Change is you are interested, because change what dictates which way the system is moving. So Cp, if you know heat capacity of any material, solid, liquid, gas, you can calculate delta H. That is what you know fundamentally need to know. What about, that's the thing, and then obviously if you know one you can calculate other, H1 is known and H2 can be calculated. That is what you need a standard state. Okay, I am not going to teach those of these. This will be taking a lot of time for me, but you who are done these courses, you will be knowing it. Okay, this is not the course for this kind of aspects. So therefore general term is this HT is H reference, that's the standard state, reference state, plus integration T reference to T, any temperature Cp dt. That is what you need to do. That is very easy to do computational way, right, in computer, provided you know all this. Okay, now nearly entropy is also related to Cp, correct, as a constant pressure you see, and that's equal to the del Q is equal to Cp dt. Okay, and that's equal to second law of thermodynamics tell you that's equal to TdS. Come on, right? This is basically heat. Del Q is equal to Cp dt. That's equal to heat, right? That's my white color chalk. That's why it's visible. And then this second law of thermodynamics tell this is TdS. So now you can write down Ts equal to Cp by T dt. Straightforward, right? There's nothing in it. Integration of that gives you change of entropy, Cp by T. In entropy it is Cp dt. In enthalpy it is Cp by T dt. This is the mistake many student does. They always try to forget this relationships. Okay. Then you can do all these things. So basically, finally it boils down St is equal to S reference plus T reference to T integral Cp by T dt. So you can get Cp values from any solid liquid gas, then you can calculate Ht and St. And that's all. Then you can calculate Gt. Once you know for every phase, every material Gt, then you are done. But that's about the bulk thermodynamics. Bulk thermodynamics means thermodynamics of big materials, where size doesn't matter. Why? Because in big materials, surface area is very small as compared to the volume, or compared to the bulk. Atoms, surface atoms are very small. So you can ignore them. It's hardly 2 to 3% of the total number of atoms sitting on the surface. So you say, I don't need them. I don't need them to be considered for my calculation. I can ignore. That will be only 1% of my calculation. So I don't need it, right? So that's what it is. So, but in nanomaterials, that's the subject of today's lecture or maybe our semester. That's not the way. There, surface area is very large. Number of atoms in the surface is pretty large, and it's a function of the size of the material. And that's why that must be considered. I said must be considered because if you ignore that, you need almost 25 to 30%, and sometimes 40 to 50% of the total energy system. It's not at all advisable to ignore that. Correct? That's what you must remember, which I have been telling you again. Now, let us come back to the concept of entropy a little bit before we move into various other aspects. You know, if I take sand and salt, so 1 minus x part of sand, x part of salt. X can be anything, 0.1, 0.2, 0.3, or 1 minus x is basically the other one. So, if I mix them together physically, the free energy system which I have given you, H minus Ts, will be behaving like a straight line as a function of x. As you keep on adding salt, 1 minus x is sand and x is salt, so these will keep on increase in a straight line way because they are physically mixed. Put the sand and salt, just rub it off or mix it together, it will never be mixed atomistically. Correct? They will be mixed physically. You can even separate them out after some time. Correct? You can pour water, sand will remain on a filter paper and salt will go into water, then water will boil it up, you can get sand, salt back. That's a classic experiment the school students always do to retrieve sand, salt from the sand and salt mixture. So they are physically mixed. They are not mechanically, they are not atomistically mixed. They are not mixed at atomic level so that you cannot separate them out. Okay, so that's the aspect of physical or mechanical mixture in which if you mix them together, the energy of the system will increase in a linear fashion as a function of the fraction of the second phase. That's it. Correct. But you know, there's a guy long back, okay, sometime in 1870s to 1880s, is known as Ludwig Boltzmann. Many of you heard about it. And this is his tombstone. Okay, let me just share a story about it. He was Austrian. He's from Austria. He worked with gases and developed Maxwell-Boltzmann theory. He worked with Stephen's law, Stephen-Boltzmann law, Gibbs law. But he was one of the finest brains in the world. Okay, he said entropy is related to probability. And then he attracted a lot of criticism, and sometime at the age of 70 or so, he committed suicide. So, but this law, S equal to K, L and W, ln is log, right? This law is a very fundamental law. It's a fundamental to everything in this world. Whether you talk about biology, to physics, to chemistry, to material science, to mechanical engineering, any field of science and engineering, this is a fundamental law. And it is so important, that's why in tombstone it is written. Okay, he lived in Vienna, he was born in Vienna, he lived there and he died. You know, this law changed everything, okay, because it's a probabilistic law. It is, we know that it is a very fundamental law now. It's almost 115 years, okay, from the death of Boltzmann. So that's okay, correct? And his father was a civil servant, and he was a brilliant scientist. He did many things, but finally he accrued a lot of criticism and he could not take it up anymore. That's what happens in science. In science, you attract, if you want to do something new, you will be cynosure, you will be kind of, attacked again and again. This has happened many times in the history of science. This happens here also. We also face the same thing. This is not true. This is true for every aspect of science engineering. But that doesn't mean that you will not do anything new. Okay? Human nature is too obvious. So she was one of these classic examples. So if you mix two things together, like if I take salt and water, mix them together, there will be a solution, right? Or if you take sugar and water, mix them together, stir it up. Many times you drink that, right? Sugar syrup. Okay. So that's the solution. Solution is atomistically mixed between the two pieces, atomic mixture. So if you do that, then phi and g will not behave like this straight line here. It will behave like a parabola going down. That's very funny, right? That's mainly because of entropy. Okay? So imagine if Boltzmann equation was not derived, we could have followed that one. I'm not saying that one, somebody else could have come, but Boltzmann was that big discovery he made. Atomic solution means it's completely mixed, nothing is separable, completely mixed at the atomic level. Okay, now, these are the slides I am using from my colleague Professor Anna Subramaniam. Okay, so I should Gibbs free energy, mixed difference is basically mixed state minus unmixed state. That we have already done. Okay. Now, depending on the values of delta H mix, there are different kinds of solutions possible. First one is that obviously this is related to bond, right? Bond, if you have two pieces A and B like salt and the water, salt is one thing, water is another thing. They are molecules. Salt is NaCl, water is H2O. Okay, so A and B. Now, if the bonds are same, bond energy is same for AB, BB, AB, A, then delta H mix is 0. It's called ideal solutions. Ideal means something which never happens in life. It is very difficult to perceive the situation. The two guys will mix, and the bond before the mixing and after mixing will remain same. Okay, this rarely happens. Delta H mix will always be not equal to 0, which is usually found in the practice. Okay, that means mixing process is either endothermic or exothermic. There will be heat producing or heat absorbing. Then we need a more realistic computation of delta H mix. That's why different models are available. Because it is non-zero, you need to then use different concept. So I'm not going to discuss about that. As most used model is quasi-chemical approach, in which you can calculate difference of bond energies after the mixing and before the mixing. In real materials, real solutions alloys, following factors comes into picture, which can lead to substantial deviation. Okay, first is that some cases these atoms can be ordered, they can be clustered, they can have strain in the materials, Then there can be substantial difference of size like interstitial solution iron carbon, right. So, there are different models, right. Now, as you know, in case of ideal solutions, delta H mix is 0. So, therefore, delta G mix is minus T delta S mix, where delta S mix is given by Boltzmann law. Okay. You can derive, okay. That is equal to minus XL and XA plus XP and XP. Thus, this log term is coming from his fundamental equation x is equal to K, L and W, where XA and XP are the mole fraction of A and B. Correct? So, therefore, if you put together T minus delta S, that is equal to RT into log terms XL and XA, right. So, then if you look at curl, this becomes a negative term, right, because XA is a fraction, XP is also a fraction. So, log of any fraction is negative. So, this value will make the energy system more negative. So, that means delta G mix will go down from 0, and that is why stability will increase. Correct, but you know, most of the cases this does not happen because delta H mix will not be 0, and many models like regular solution model, quasi chemical model says delta H mix is equal to this, right, where sigma is basically interaction parameter, how strongly these atoms are bonded, okay, how strongly you are bonded with your friends, same thing, that is what it is. So, then delta G mix is equal to this term plus RT XA ln XA plus XP ln XP. That is it. So, if you, that means the delta G mix value will depend on the relative values of these terms, the sigma X XB and the relative values of the entropic term. So, that is, there are a lot of many situations possible, right. Let us not discuss about that. This is the brief introductions of the solutions, free energies and how they are related. Okay. Now, I am going to discuss few important things about solutions, right. What? First thing I am going to discuss about is chemical potential, right. Okay, you know, when you talk about solutions, most important aspect coming to picture is mind. Yes, so that is what we started with, right, ice water mixture. What dictates the stability, the equilibrium between ice and water mixture, the interface? It is the chemical potential. So, you must be wondering what is this. Let us go back, okay, let us go back there. You know what is chemical potential? Well, when you know chemical potential, any thermodynamic system, chemical potential is nothing but amount of energy absorbed or released per unit mole. That is it. What is that? Let us come back. You know, the way chemical potential is defined is this mu. Mu is defined, is used as a chemical potential. Well, let me just start with that. You know, when I say suppose if I say you have potential to become prime minister of this country, what does it mean? That means we have all the abilities to become the prime minister of the country. When you talk about potential of any atom in a solution, that means ability of that atom to react with the other PCs in the solution. If the species A has ability to react with species B, this ability is defined as a chemical potential. Remember that. Forget about all the mathematics. This is the physical meaning of that. So, chemical potential has the same meaning as you see here. It is chemical because they are related to reaction, that is why. So, mu is basically defined as del G by del this is has to be species A del Na, right, at constant temperature and pressure. That is why it is defined. So, that means if I take a huge solution, I add only 1 mole of A into it, the change of energy per unit mole is known as chemical potential. You take this big room, okay, and add only 1 molecule of oxygen atom. The change of the energy per mole of this mixture, it does everything. It has carbon monoxide, carbon dioxide, oxygen, nitrogen, moisture, argon, I am adding one molecule of oxygen, a change of this free energy. That will be very small, right? Obviously, that is why at a constant temperature and pressure. That is what is known as a chemical potential. Okay, now, so you have to do a process called addition or subtraction of molecule. Then you can measure the change. That is what it is defined. Now, if you assume a fixed entropy and volume actually, then we can always write down. We can always write down dG basically equal to mu dN. Right? This is nothing but same thing here. All right? This should not be GA. It should be only G, because free energy of system, right? Not A. That is what it is. So now, as you know, we have already written what? We have already derived actually, not written dG for single component system VdP minus SdT, right? So in a solution, this must be, this is for single component like water I have done, right? But when a solution, this has to be modified because we need a chemical potential change, and that is written like this: n equal to n mu y. You have many components A, B, C, D, F, G, H. In a solution, they are like in this gas mixture, you have so many components, like you have oxygen, nitrogen, I showed you. So you have to consider everything here. The changes of chemical potential, the changes of the free energy has to be related to all effect of all this aspect, like mu y dni, mu 1 dn1, mu 2 dn2, mu 3 dn3, like that. Correct? That's the difference between the single compound system and a solution, right? Single component, this Ni is 0. There is only one component. There is no solution, pure water. So there is nothing in it other than water. So water, mole fraction of water, 1. There is nothing. So therefore, this term goes to 0, dni term, and we can ignore it. But in a solution between this gaseous mixture, or suppose salt and water or sugar and water, this term cannot go to 0. This is the finite value of dni. So that's why you need to consider this aspect, right? That's good. So far so good for a bulk system in which size is not important. Okay. So I write down this as a bulk. What about nano? We already discussed, right? You cannot ignore the surface area. This has to be modified then. How it is has to be modified? Very simple. What is this term? Gamma dI, right? Gamma into dA, that is the surface energy. Basically gamma into A. So if you have suppose many surfaces, then each surface has different energies. It's at different areas actually. So you have to multiply with that. So, and each surface can also different energies. Suppose in a cubic crystalline material, 1 facets has one energy, 1 0 facets another energy, 1 0 facets different of energy. So you have to add it up. So this is going to be this equation now. Remember that. We started with at the last lecture with dG is equal to VdP minus SdT, right? That's what this equation is. And then we landed up a new equation. We have added chemical terms, we have added surface energy terms. That is what is not difficult to understand, very easy to understand, right. So, therefore, what I can do? So, I can write down chemical potential and nanoscale as two parts. One, this is for the bulk. At the moment I write infinite, that means bulk. Bulk means size is very big, and surface energy, right. Surface energy term to be written gamma, right. Okay, let us erase it and write properly. Right. So, you can see that is the fundamental law, correct. So, this is the bulk chemical potential, this is known as surface potential. Bulk chemical potential, surface potential, right, correct. And this gamma is surface energy. So, now we can always, okay, let us erase it up some of things. We can always just like in the last lecture, we can always do a simple math by using a spherical size. You must be thinking, sir, always a spherical size, because spherical size is something which helps us to do the mathematics very clean and understandable. So, mu gamma is what? Gamma dA by dN. That is obvious, it is coming from this equation, right, coming from that equation which I derived, this equation. Okay, you can see that if I take gamma dA by dN, the del G by del N is nothing but gamma dA by dN. Okay, you remember, no? Mu is defined as dG by dN I, temperature, pressure, I is any component. So, therefore, if I take that for nanoscale, it becomes dA by dN, gamma remains constant, right, remember that. And dA is for a spherical particle is what? d of 4 pi r square, that is nothing but 8 pi r dr. I think we should be careful about that I and gamma. I should write it properly, otherwise this also, right. Am I clear? So, now then what is dN? dN is basically 4 pi r square by Vm. Vm is the molar volume of 1 mole. Okay, that is the number of atoms, change of number of atoms. Okay, dN 4 r square by dr, and dA is that, right. Am I clear? Not clear. Well, what is N? Okay, let us erase this equation. You must be confused. What is N? Okay, let us not write N. V is equal to 4/3 pi r cube is the volume of one atom multiplied by the number of atoms. Okay, that is the total volume, correct. So, then dV is what? 4 pi r square and dn, correct? So, dn is 4 pi r square by dv, which I have written is molar volume, into dr correct, right. So, then find upon knowing this, let us do to complete the maths. I like to do this. This gives me feeling of erasing the board, right? Correct. So, by doing some kind of mathematical operation, which is very easy actually, you can put gamma here, dA is known, dN is known. So, mu gamma is equal, mu, yes, mu gamma is gamma, dA is 8 pi r dr divided by 4 pi r squared, 4 pi r squared, 4 pi r squared Bm dr. So, you can see this becomes twice gamma Bm by r. This is very good for a sphere actually. Okay. So, this is mu r. Mu r is basically gamma multiplied by dA by dN, and dA is for a spherical particle is 8 pi r dr. You know, volume of the particle is basically 4/3 pi r qn. Okay, now you can write down dV by dr, yes, dV by dr, that's equal to 4 pi r dn. So, dn is equal to 4 pi r square, oh, this is r square, yeah, 4 pi r square by Vm into dr. That's, then I plug in all these things, I plug in this, let us write down 3, this is 2, this is 1. So, I plug in, you know, in 1 the dA term and dN term, I get this, correct. So, therefore, mu, total mu is obviously mu infinity and mu gamma. So, mu infinity plus twice gamma Vm, right. This is a fundamental equation, you must remember that. Okay, always remember, don't forget at all. This will be used in our future descriptions, many of these future descriptions. So, therefore, by increasing the spherical radius, chemical potential of small systems can be increased. That means, by reactivity can be increased, potential can be increased, that means reactivity can be increased. And you know, this term twice gamma by r is known as a Laplace pressure term. This is exists in Bowell experiment also. This can be converted to Laplace pressure. So, pressure and volume, you see mu is equal to mu infinity delta P into Vm. That is how it can be treated. This is done by Laplace actually. So, this is one derivation which I thought you should know very well. Okay, now let me go back. You know, chemical potential can be derived or can be obtained very easily by knowing this free energy composition curve, which is a parabola, and then drawing a tangent at any point wherever you want to know the chemical potential. So, here is x, and if you draw a straight line or a tangent to this curve at this point, it will hit the vertical axis, and wherever it hits, you get mu A, chemical potential of A and chemical potential of mu B you can get. That is something which is done in typical thermodynamics. And then once you know mu A mu B, you can measure the G is equal to 1 minus x mu A multiplied by x mu B, right. This is also very standard, because the two chemical potentials of A and B components for phase alpha, you can do that. Well, why it is so important? Because it tells you the stability conditions. So, in ice water mixture, so for the water, chemical potential in ice must be the chemical potential of the salt in the ice, right. Similarly for water also, okay. This should be beta, right. That is it. Okay. So, I will not discuss further, except that we will show you a picture of ice water mixture. Now, question is this, for the last whatever time I have, let me come back here. Not only that, this is the something which chemical potential modification is done. So, for a nanostructure system, you can clearly see how it is modified. This will also an effect on the compositions of the solutions. Solution, right. So, you can have nanoparticles of alloys. The chemical compositions of the two PCs A and B will also depends on the curvature or the size of the particle. And this can be easily derived. How? Well, let us do that. That is very easy to do. I think it can be done in 10 minutes or so I have. So, G, suppose any phase alpha, G is obviously N alpha, and then this is for the bulk, okay. Oops, why I always and you have a surface energy term, and this is what it is. Am I right? So, if I consider a spherical particle, correct. If I consider a spherical particle, 4/3 pi r cube, volume of each atom, okay. The spherical particle size is this. Number of atoms is A, and each atom has volume, atomic volume, suppose. This is the atomic volume of B alpha, correct. So, then this will be N alpha, correct, which I have written. So, N alpha is equal to 4/3 pi r cube P atomic volume of alpha. Atomic volume means volume of a single atom, okay. Then number of atoms is equal to volume of this spherical particle. That is understandable, right. This is volume of a sphere, and each sphere contains n number of atoms of alpha, and then volume of each atom is V atom alpha. So, this multiplication must be equal to this. So, now we can write down dn beta by dr, that is equal to 8 gamma r square by V atomic alpha, right. That is easy. Now, let us take up this equation, right. So, we can always write down mu beta, that is equal to mu alpha y beta I must be careful enough. This should be alpha, why it will be beta, correct. So, that is equal to, come on, we are talking about alpha phase, we are writing beta phase. Correct. We can write down this assuming gamma to be constant. Gamma is not depending on number of atoms or anything, right? Gamma has to be constant. This is nothing but if I derive this equation, okay, take a derivative of this equation with respect to n alpha. So you can see n alpha and now get constant, okay, cancel, this becomes G alpha bulk plus gamma dA alpha dN alpha, right? So you can write down this very simply. Gamma I can do that or I cannot do that. You can do that actually. Okay. So this can be written gamma. What is G alpha by D gamma? What is G alpha by the way? D alpha is for a sphere is 4 pi r square. So what is G alpha by dr? Okay, you want me to do it? And what is this? dr by dn alpha, that is opposite of this term, dn alpha by dr. So d there's a mistake here, right? You could see that. That's what I want you to point it out. This should be 4. 3 would get cancelled, this will be 4, right? So these mistakes I would like you to point it out. So this becomes G bulk plus twice gamma okay, that's clear to you. This is the thing which you already derived. So now then I can write down mu alpha this is atomic volume of alpha, right? That's what you should know. Right? So that's obviously will be equal to, remember this is the reference we have taken, that's obviously will be equal to entropic term, entropy change term, 1 minus x, right, xa ln xa. So if I write down xp as x, then 1 minus x ln 1 minus x plus x ln, okay, I think we should be doing this carefully because we are talking about the surface composition versus this, the bulk composition. So this is, okay, let me write down better way. So what did I write? That's equal to x 1 minus x multiplied by log of, this is the surface composition with a particle size r. The equilibrium means thermodynamic equilibrium obviously, otherwise everything will be invalidated, and divide by 1 minus x equilibrium infinity. This is for the bulk. Okay. So, surface with respect to the bulk, that is what we are doing here, no? Bulk and surface, right, and then log of, and this is plus x log of x r equilibrium by x. This is nothing but an entropic term because of the variation in the composition of the surface and the bulk. Okay, now, if you simply consider x to be 1, then single phase basically, x to be 1, then the mathematics will be very simple. Why x to be 1? Because you are considering single x 1 means what? Pure, right. So, when x equal to 1, x become 1, then this become this twice gamma V atomic alpha divided by r. This becomes what? This becomes, this term becomes goes to 0, x is 1, so this become goes to 0. So, x is 1, so that also goes to 1, right, log of x r equilibrium by x infinity equilibrium. Okay. Why you assume x equal to 1? That is easy, because x equal to 1 gives you pure phase, right. That is why. So, then you can see x r equilibrium is equal to x infinity equilibrium into exponential twice gamma p atom alpha. So, this is the composition variation as a function of particle size r from the surface to the center. Okay, let us stop here. We will come back in the next lecture. I think I have discussed enough. We will again discuss this part again. Thank you.